Here we are in section 3.3. We had just gotten our first two shortcuts, differentiation rules, the power rule for powers of x, and then the derivative of a constant, which is always 0. And now we'll look at some derivative properties that bring these together. So our first property is going to be the constant multiple property. Now, you don't need to memorize the names of these properties so much as knowing how to use them. So this constant multiple property is what happens when we are taking the derivative of a function that has been multiplied by some constant. So we're going to say c is our constant times some function f of x, whatever that might be. Okay. And what this property says is that if you're taking the derivative of a constant times a function, it's the same thing as if you just took the constant and multiplied by the derivative of the function itself, d dx of f of x. Okay. And to see why that works, because, you know, you should verify that things are legit, all right? Don't always believe everything you hear, but this one's going to work out, and here's the proof. So if we take our left-hand side of that equation, our starting statement, the derivative of a constant times a function, we can put this straight into the limit definition of the derivative, where this all stems from, and see what's going on here. We can take the limit as h approaches 0 of c times f of x plus h minus c times f of x over h. Okay. And we're going to be able to factor out that c in the numerator, the constant. So we're going to have c times f of x plus h minus f of x over h. All right, let me make that into parentheses. There we go. So constant times that expression. We're just factoring out the constant. And then what this comes back to, it's been a little while, I think, but this comes back to the limit laws. Those are way back in chapter 2. Oops, limit laws. And one of those limit laws says that if you have the limit of a constant times a function, it's the same thing as taking the constant times the limit of the function. So we can take that c outside of the limit statement. C times the limit as h approaches 0, f of x plus h minus f of x over h, which hopefully now we all recognize this right here to be the definition of the derivative of f of x. So what we've come around to is that this is c times the derivative of f of x. Okay, just like our constant multiple property says. Okay, so there's our first derivative property. And now the second one is going to be the sum property and the difference property kind of rolled together here. These are very similar to each other. So this is kind of two properties in one here. If we're trying to take the derivative of a sum of two functions, f of x plus g of x, okay, it turns out that that is going to be the same thing as taking the derivative of those two functions separately and then adding those derivatives together. So d dx of f of x, derivative of f of x, plus the derivative of g of x. Okay, so that is the sum property, and then the difference property just does this exact same thing for subtraction. So if it's a minus here to start, f of x minus g of x, and you're taking the derivative, take the derivatives of f and g and subtract them like so. Okay. Now, don't believe everything you see. Let's prove this. Proof. All right. So let's write the derivative of f of x. Let's do the sum property here. The proof for the difference property would also go very, very similarly to this. Just change all the pluses to minuses. Okay. So if you're doing the derivative of f of x plus g of x, this is like a new function that you're creating there. So when we use our limit-based definition, the limit as h approaches 0, when you do the x plus h part of that definition, we're going to have f of x plus h plus g of x plus h. Okay, so that's the first thing going in here. F of x plus h plus g of x plus h. Okay, so there's our x plus h part, and then minus the function with just x. So f of x plus g of x. Okay, all over h. And then let's see what we've got here. Limit as h approaches 0. Let's go ahead and distribute this negative here. F of x plus h plus g of x plus h minus f of x minus g of x all over h. Okay. And I think I might run out of room here if I don't scoot this over a little bit. So let's shrink it and scoot it just a little. Thanks, technology. Okay. Next step. We're having our limit as h approaches 0. And up in this numerator, we're going to group together our terms that work with the function f of x, or x plus h, and then our other terms that have the function g of x and g of x plus h. Okay, let's do the f's first. F of x plus h minus f of x, okay, plus g of x plus h minus g of x. Oof, barely squeezed it in there, all over h. Okay, so now what we're going to do here is we're going to split up this single fraction. Okay, so we're going to have limit as h approaches 0, and we're going to put our f terms in one fraction. So f of x plus h minus f of x over h. And then we're going to add g of x plus h minus g of x over h. All right. So we're taking the limit of those two fractions now added together. Notice how we could do that because these fractions still have the same common denominator. If you were to recombine these, you would just end up right back where we were. Okay, so don't let that trip you out too much. Okay, and so what we've got here is another opportunity to use a limit law. Limit law. Okay, which says if you're taking the limit of the sum of two things, you can just take the sum of the two individual limits. So we can put a limit as h approaches 0 on this first term, the first big fraction with the f terms. And then we can put a limit on that second fraction with the g terms. So get that rational expression in there. Okay, and then if we look at each one of these limits individually, this right here is a definition that we're getting very familiar with. That is the definition of the derivative for the function f of x. So we got d dx of f of x. And then this guy right here is just literally the exact same thing, but with a g instead of an f. So this is the derivative of g of x by definition. So d dx of g of x. Okay, which, check it out, turns out to be exactly what we were saying it was according to this sum property. So there it is, verified that the sum property does actually work. And again, you could go through this proof for the difference property as well, just putting a subtraction in instead of the addition right here initially. All right, so there you go. Those are the constant multiple, sum, and difference properties. In the next video, we'll put those to use.